Hey everybody. So today begins lesson 4 in trigonometric equations and identities. This is where we're going to begin working with specifically with identities and how to simplify them. Now, if you are lost and trying to figure out where lesson 3 went, lesson 3, if you look at each well, is just set up for a review of solving trigonometric equations. So there's no note, which is why there was no video for lesson 3. But here we are with lesson 4, and we're going to take a look at simplifying trigonometric identities. Now, this fella, your formula sheet, is now going to be your Bible. Okay, you need to have a printout version of that through every question that you do here. Okay, super, super important. Okay, so as a way of a little introduction, just a quick review. We're going to solve sine squared of theta plus pi over 4 equals 1 in the domain 0 is less than or equal to theta is less than or equal to 2 pi. Now just take note of the little icon there. This is not in your book yet. I just thought we would review it just as a way of introduction for today. So we want to square root both sides. Remember, when you square root both sides, it could be plus or minus. So I end up with sine of theta plus pi over 4 equals plus or minus 1. Now, I know when sine of something equals plus or minus 1. If I go back to my unit circle, always go back to your unit circle. Calgary Stampede, sine is your y value. When does sine equal plus 1? Well, we have a y value of plus 1 at 90 degrees, or at pi over 2, because we're talking in radians here. And at 3 pi over 2, we have a sine value of negative 1. So I know that my angles here, the thing that would go, now watch this very carefully. I'm just going to put on a little highlighter here. The thing that would go in here would be those two answers, so pi over 2 and 3 pi over 2. So what we do is we say that theta plus pi over 4 could equal pi over 2, or theta plus pi over 4 could equal 3 pi over 2. Okay, so I'm just going to clear that and we'll continue on with the slide. And there I go. I've got theta plus pi over 4 equals pi over 2, and theta plus pi over 4 equals 3 pi over 2. Because pi over 2 and 3 pi over 2 would give us the ratios of plus or minus 1 that we were originally looking for. Now, I need to solve for theta though. So now, because it doesn't just say theta, it says theta plus pi over 4, I need to get rid of the pi over 4. So I just subtract pi over 4 from both sides. If I'm going to take pi over 2 and subtract pi over 4, I can do that in my head. I just want to think about pi over 2 as a fraction over 4. Pi over 2 is 2 pi over 4. So 2 pi over 4 minus 1 pi over 4 is 1 pi over 4. So that gives me theta equals pi over 4. Likewise, over here, I got to think of 3 pi over 2 as a fraction over 4. So 3 pi over 2 would be 6 pi over 4. I end up with 6 pi over 4 minus 1 pi over 4. So that would give me 5 pi over 4. Once I've done that, once I've actually figured out theta, I always want to just double check that they are still in my solution set. Both pi over 4 and 5 pi over 4 do exist within this 0 to 2 pi range. So that is totally cool. Okay, so my answers are pi over 4 and 5 pi over 4. I just mentioned that because sometimes doing that last step will bounce you out of the domain. Then you either have to just not include it, or you have to think about a coterminal angle that might exist there. Okay. So now what we're going to do is we're going to start talking about identities. So I am in your book now. This is the beginning of simplifying trigonometric identities. Identities, a trigonometric identity is an equation that is true for all permissible values of the variable in the expression on both sides of the equation. And what we quickly want to do is just go through a bunch of different categories on what kind of groups of identities that we're going to deal with. Today, we're really only going to get down to, if you look at your formula sheet here, okay, we're only going to get down to about here. So we're only going to look at maybe even the top third. And we're actually going to spend a couple of lessons just in those top third. That top third collectively is called your fundamental identities. And they are divided into 4 kind of subgroups, okay? So first one is your basic identity. Now your basic identity are really your primary trigonometric ratios. So sine of theta, cos of theta, tan of theta. These are the things that are not given to you on your formula sheet. By the time you hit 30-1, we assume that you would feel very comfortable with these guys. So sine of theta, cos of theta, and tan of theta. After that, we start going into your, the ones that are on your formula sheet. We have your reciprocal identities. Well, we've already talked about these guys. Your reciprocal identities are the cosecant is the flipped version of 1 or of sine, so it'd be 1 over sine. The secant is the flipped version of cos, so it'd be 1 over cos theta. And cotangent is the flipped version of tan, so we say 1 over tan of theta. So these three are on your formula sheet as such. Then we have the quotient identities, and the quotient identities involve tan and cotangent, but writing them in relation to sine and cosine. So tan of theta is sine of theta over cos of theta, and cotangent of theta is cos of theta over sine of theta. Okay, so I'm assuming you followed me all the way along and have filled in all those blanks on your own notes. Remember, if I'm going too fast, you have the ability to shut me up by pressing the pause button. Pause, write it all down, and then we can continue together. I guess that's the one benefit of a video is you have the ability to shut me up. You don't have the ability to shut me up when I'm in person. Okay. Okay, gotta focus. Pythagorean, oh yeah. As a quick aside, and this is in your notes as well, I just wanted to mention some wording here. So we have told you two different things for the cotangent of theta. We've said that you can write cotangent of theta as 1 over tan of theta, but we've also said you can write cotangent of theta as sine of theta over cos of theta. Just a little phrase for you here. These are said to be birational equivalents. They're not an inequality because they actually have different non-permissible values. One of the things students struggle with here is defining what the non-permissible values are. We're going to do lots and lots of practice on that, so don't stress. But if you look at the first one, cotangent of theta equals 1 over tan of theta. Well, think of it this way. You remember that tan of theta is sine over cos. So if I just wrote that, I'm going to get rid of this for a sec. If I wrote that as cotangent of theta equals 1 over sine of theta over cos of theta, because that's what tan is. Just to kind of bring this home for a second. Cos of theta can't be 0, because if cos of theta was 0, this little guy would be undefined, and 1 divided by undefined is undefined. But sine of theta can't be 0 here either, because if sine of theta was 0, I'd get 0 divided by something, which is 0, but then overall in this fraction, that would leave me with 1 over 0. So in the first one, both sine of theta can't be 0 and cos of theta can't be 0. In the second one, and here's what I want you to notice, with cotangent being sine over cos, we, pardon me, we would just say cos of theta can't be 0. So that's where this slight difference is, and that's why we can't call it an equality, okay? Because they have slightly different non-permissible values to them. Okay, so then we start with the Pythagorean identities. To start with the Pythagorean identities, we start with the equation of the unit circle. X squared plus y squared equals r squared. Now, the unit circle itself was 1 squared. But what we're going to do here is we're going to just divide everything by the radius first, okay? So if I divide it by r squared, I ended up with x squared over r squared plus y squared over r squared equals r squared over r squared. Now, this guy, you know right away, is 1. X squared over r squared. Well, do you remember in any conversations that we've had where you see x over r, where you see x, that adjacent, over r, that hypotenuse? X over r is really the cosine. Go back a couple, actually just go back to the top of your page where you wrote basic identities, right? And y over r is sine. So x squared over r squared is cos squared, and y over r all squared is sine squared. So we end up with a Pythagorean identity that says the cos squared of theta plus the sine squared of theta equals 1. Okay, so anytime you see the cos squared of theta plus the sine squared of theta, you can actually now just replace that with 1 because that's a valid statement. That's what an identity means, is it's a valid statement. It's something that I can replace one thing for another because they're the same thing. This is one of the reasons I love trig identities, is really it's just a bunch of puzzles. You have to put a piece here into here, you have to put a piece here into here, and that's all you're doing. Just think of it like a puzzle, okay? So that's the first Pythagorean identity, is cos squared plus sine squared equals 1. Now, from there, if you look at your formula sheet, you actually see 3 identities that kind of look like a squared plus b squared equals c squared. I've only dealt with the first one. The other 2 come from that first one. So what we can do is we can either divide everything by cos squared or divide everything by sine squared. First thing we're going to do is divide everything by cos squared. So I just took this guy here and I divided every term by cos squared. That gives me this light blue guy. Well, cos squared theta over cos squared theta is 1. Sine squared theta over cos squared theta. Sine over cos. Which one is sine over cos? Well, that's 10. And then 1 over cos, the flipped version of cos, is secant. So we end up with 1 plus tan squared theta equals secant squared theta. Okay, so that's another identity that we can use in some of this stuff. The other way to do it is we go back to the original, this cos squared theta plus sine squared theta equals 1, and we divide everything by sine squared instead. So if I divided each term by sine squared, now I'm looking at this guy. This is cos squared theta over sine squared theta. Well, cos over sine is cotangent, so cos squared theta over sine squared theta would be cotangent squared theta, plus 1 equals cosecant squared theta. So that's the third Pythagorean identity. Okay, so 1 up here, 2 right here, and 3 right here. And that's actually where we're going to stop as far as introducing identities. For now, we're going to spend a couple of days now just working on simplifying and then verifying and then proving, okay? And today is really just about simplifying. It's really just about starting to feel comfortable, A, finding your NPVs, and then B, trying to figure out something to do with what's in front of you, okay? So now I just said these words, so I might as well introduce them to you and just start some formal definitions here. So to verify means you're showing the identity holds for a specific value, okay? The easiest thing to do to verify on your diploma or a multiple choice question is just plug in a value. So you can either do that by hand, just pick a value and plug it in for theta or for x or for whatever, and show that the left side equals the right side. But if it's a multiple choice question, I would even just store your value in your calculator, and then you can just type it in your calculator. So the store feature on your graphing calculators, if you're a Casio, it's the little arrow that's pointing to the right underneath the tan button. And if you're a TI, it's the STO button, which is on the left side near the bottom of your calculator, okay? All right, now, sorry. Little glitch there. Okay, so a value for theta. So the easiest thing to do is to verify on your diploma or a multiple choice question is to store a value for theta or to graph the two functions. Then we have prove. Prove is showing that the identity holds for all values of theta. We must be good at fractions because our calculator won't be of use here. So that's kind of a nice segue into let's deal with fractions for a sec. Let's just go through some questions, make sure we're comfortable with some fraction rules. So it says simplify the following expressions, state the non-permissible values for the variables given. So I have y over x plus x over y. First of all, non-permissible values, what is not allowed to happen? Well, x can't be 0 and y can't be 0 because both of those appear on the bottom of a fraction, and that's a no-go. So x and y can't be 0. Now, to add fractions together, I need a common denominator. So essentially, my common denominator here is going to be xy. This first fraction is missing the y on the bottom, so I multiply it by y over y. And then this second fraction is missing the x on the bottom, so I multiply it by x over x. Remember, when you're dealing with fractions, whatever you do to the bottom, you have to do to the top. So that gives me, when I multiply this guy by y over y, I end up with y squared over xy. And this guy, when I multiply x over x, I end up with x squared over y. sorry, over xy, which gives me this, the y squared plus x squared all over xy, okay? Next guy, x plus y over x minus x plus y over y. Now again, non-permissible values. I know that x can't be 0 and y can't be 0. And again, I'm looking for a common denominator. So my common denominator here will be xy. I'm missing the y here, so I'll end up with a y over y that I'm multiplying in here. Just remember, when you do that to the top, the y that you're putting on the top is going to end up getting distributed to the x and to the y. Same thing over here, except what's missing on the bottom is an x, so I'll multiply this by this guy by x over x, and that will mean an x gets distributed to the x here and to the y here. So we're looking at something like this, okay? The y gets distributed to the x and to the y. That x gets distributed to the x and to the y. A reminder that that's a negative, so the negative also gets distributed. So we're looking at now xy. When you have two letters together, you're just always putting x first because it's in alphabetical order. So xy plus y squared minus x squared minus xy. Anything I can clean up here? For sure, I've got an xy and a minus xy, so that adds to 0, and I'm left with y squared minus x squared over xy. Just a friendly reminder, lots of kids look at something like this, and I was thinking about saying this in the last example, and I didn't, but lots of kids look at this and say, hey, okay, why don't I cancel out one of these x's? You can't do that because you're not dealing with the same thing here. This whole guy is one item, y squared minus x squared. You would only be able to divide that out if you saw a y squared minus x squared on the bottom as well. Okay, so you have to be really, really careful that you know when you can divide something out and when you can't divide something out. If we take a look at 1 over xy plus x over y, the common, or let's talk about NPVs first. So x can't be 0 and y can't be 0 again. Then we're looking at, okay, a common denominator is going to be xy. This one's already set up as a common denominator, so I don't need to touch him. This guy, I need an x on the bottom, so I put another x on the top as well. That will give me x squared over xy. So I'm left with 1 plus x squared over xy. Okay, now this guy makes everybody shiver at first. This is called a complex fraction. The reason it's called a complex fraction is because you have a fraction within a fraction. You're going to see lots of these with the trig stuff as well, and I would strongly, strongly encourage you, don't leave it like this. It's really hard to see what's going on vertically. Write it left to right instead. Remember, let me just put my highlighter on here for a sec. This overall fraction here, you've got this guy divided by this guy. So just do that. Just write it as that division statement instead. Okay, so I just took the top and I divided by the bottom. Now, NPVs, take a look at this guy for a sec. It's okay for x to be 0. It's okay for y to be 0. What we can't have is 0 on the bottom of a fraction. So that tells me x can't be -1. Okay, that's what would cause a 0 on the bottom of a fraction here. Okay, now, in order to divide fractions, I have to multiply by the reciprocal, so I'm going to rewrite this as multiplication, and then I flipped the second fraction. Here is a great example of something I'm allowed to do now. I have x plus 1 and x plus 1. They divide each other out, okay? Because x plus 1 divided by x plus 1 is 1, and 1 times anything is itself. So that's why I'm able to divide these out now. They are the exact same binomial on the top and on the bottom. That would leave me with x plus y and just x plus y, because it's x plus y over 1, but I don't need to say over 1 there. Okay? All right, so that's all we're doing. Piece of cake. We're going to do the same thing now, except it's going to have trigonometric ratios involved. Okay, so the first one, sine squared theta plus cos squared theta minus 1. The very first thing you want to do is you want to say, okay, what restrictions am I dealing with? Well, for this one, there is no fractions here, so there is no division of 0. So there's no possibility of a division of 0. So there are no restrictions. Okay, now you don't have to actually say that. I just, because this was the first example, I want you to get kind of into the groove of thinking about restrictions, and that's why I wrote that. Now, go to your formula sheet and say, what do I know? Do you see anything on this slide that's friendly and you see it on your formula sheet? Well, I see this staring at me on my formula sheet. Sine squared theta plus cos squared theta is 1. So anytime I see sine squared theta plus cos squared theta, I can change that to 1, which means I'm looking at, which means I'm looking at 1 minus 1, which is 0. Okay? See? Easy. First one done. You got this. Okay. Next one. So, secant of theta over tan theta plus 1. Couple of things we need to talk about with restrictions. First of all, I see secant. Secant is 1 over cos. Actually, I'm going to write some of these down before I show them to you on the slide, just so we can talk about them. So, secant is 1 over cos. That means cos of theta can't be 0, and we'll figure out what theta is in a second. Then I see tan. Tan is sine over cos. So that means cos of theta can't be 0. Well, I've already stated that. But then overall on the bottom, I also see tan of theta minus 1, which means tan of theta can't be negative 1. So those are the two that I have to deal with. Those are the two that I have to solve to actually state what my restrictions are. This is not enough to state the restrictions. I have to say what theta can't be. I can't just say that cos of theta can't be 0. I have to say when that happens. Well, remember, Calgary Stampede, cos is your x value. When does your x value equal 0? Your x value equals 0 at pi over 2 and 3 pi over 2. Okay. When does tan of theta equal negative 1? Well, negative 1, that's your pi over 4, but if I'm negative, I'm in quadrant 2 and in quadrant 4. So that would be 3 pi over 4 and 7 pi over 4. So cos of theta can't equal 0, tan of theta can't equal negative 1. That's at pi over 2 and 3 pi over 2. That's at 3 pi over 4 and 7 pi over 4. Now, I have to put that together into a general statement. These are two different general statements I would make here. So I would say that theta can't equal pi over 2 plus pi n. That takes care of this guy. And 3 pi over 4 plus pi n, that takes care of this guy here. Okay, so those are my NPVs that I have to state. Those are my restrictions. Now I'm going to get on to solving the problem. Sometimes, not always, but sometimes it's helpful to rewrite this in terms of sine and cosine, just so you're not dealing with so many different things. So what I've done is I've said secant of theta is 1 over cos of theta. And then remember that big line there for that fraction is really just a division statement. So I'm dividing by sine of theta over cos of theta, that's my tan, plus 1. So now I'm going to work on this guy and clean him up. I can't change this to multiplication until this is all one fraction. So the very first thing I have to do is make that all one fraction. I'm going to call my 1 cos over cos, cos theta over cos theta. Be careful. I know when I'm saying that, I'm talking quick and I'm saying cos. Don't ever write cos by itself. It's cos of theta. If you ever write just cos, you're going to get marked down because that's really bad communication. So I'm going to call my 1 cosine theta over cosine theta. And that would give me this. Sine of theta plus cos of theta all over cos of theta. Now I'm ready to change this to multiplication and flip the second fraction. So that'll be 1 over cos of theta times cos of theta over sine of theta plus cos of theta. I now see that my cos of thetas would divide each other out here and here. And so that would leave me with 1 over sine of theta plus cos of theta. And there's actually not much more I can do with that. So we're going to call that simplified. Okay, so that one got a little bit messier. That's fun. Okay, now tan of A, cotangent of A, plus sine of A, cosecant of A. First of all, let's talk restrictions. If I see tan, I know that cos of theta can't be 0. If I see cotangent, I know that sine of theta can't be 0 because there's a sine of theta on the bottom. And then I see cosecant, which is 1 over sine, so sine of theta can't be 0 again. So overall here, both sine of theta can't be 0 and cos of theta can't be 0. Now, the first thing I did here was I rearranged everything as sine and cosine, just so you could see what I just said to you. Cos of theta can't be 0, sine of theta can't be 0. I should really be saying a there. Sine of a can't be 0, and then sine of a can't be 0. Okay, so sine of a can't be 0 and cos of a can't be 0. Well, sine of a is 0. When is sine of a 0? Remember, sine is Calgary Stampede, y value. So I have 0 on my y value here and here. Okay, so I know that these guys are out right now. Him and him. Cos of theta can't be 0. Well, that means this guy's out and this guy's out. So altogether, I can say that in one statement. It's 0 plus the period of repetition. Well, what's the period of repetition? That's pi over 2. So I don't say 0 plus, remember? So I just say pi over 2n, where n is a member of the integers. Okay? Now, I can start simplifying things out. I see that my sine a's here will divide each other out. My cos a's will divide each other out, which leaves me with a 1 for this guy. Some of you may have looked at that and said, hey, why couldn't I have gone cotangent is 1 over 10 and just divided them out that way? Totally fine, okay? One of the things which is nice, and sometimes which kids hate about identities, is there's more than one way to do things. There's lots of different ways to arrive at the same answer here. Then, sine A over sine A, which is this guy, is also going to give me a 1. So this actually simplifies to 1 plus 1, which is 2. Okay? Awesome. Okay, the next guy is secant of theta over cosecant of theta. Okay, so again, secant is 1 over cosine, and cosecant is 1 over sine. So this is the same non-permissible values as the last question. Both sine of theta and cos of theta can't be 0. And so we're looking at theta can't be pi over 2n, where n is a member of the integers. Now, then I took this and I just switched to sine and cosine. So secant was 1 over cos, and then I'm dividing, that's what that line here means, dividing by 1 over sine. When I divide fractions, I multiply by the reciprocal, so that's going to be 1 over cos times sine over 1, which ends up being sine of theta over cos of theta. Well, what's sine of theta over cos of theta? That's tan of theta. So we were able to simplify that guy into one trigonometric ratio. Okay, good. Now, secant of theta, sine of theta, cotangent of theta, all over tan of theta, cosecant of theta. Okay, so secant is 1 over cos, so cos of theta can't be 0. I see cosecant as well. Sine of theta can't be 0. Cotangent and tangent are already taken care of because we've already said that sine of theta can't be 0 and cos of theta can't be 0. So same NPVs, same restrictions that we've had on the last two examples. Now, I'm going to write this as a left to right division statement, and while I do that, I'm going to kind of switch these to sine and cosine. So my secant here is 1 over cosine of theta times sine of theta over 1 times cos of theta over sine of theta. Then I divided by tan, which is sine of theta over cos of theta, times cosecant, which is 1 over sine of theta. Now this looks messy, but it cleans up very, very nicely. Take a look at this first guy. Okay, let me get a highlighter on for you here. And I see that my cos will divide out. I see my sine divides out, so that's going to leave me with a 1. Over here, I see that the sines will divide out, and I'm left with 1 over cos. So I'm looking at now a statement that says 1 divided by 1 over cos. Well, that's the same as saying 1 times cos of theta, which is just cos theta. Okay? All right. Secant x over sine x minus sine x over cos x. Now, secant is 1 over cos, so cos can't be 0. I have a sine on the bottom, so sine can't be 0. So I start with those guys. Don't get kind of lulled into thinking this is always the restrictions. This is common restrictions, but you always have to check because it's not always going to be this. You always have to look at what would cause a 0 on a denominator. That's what you're always looking for there. Okay, so the first thing I've done here, whoopsie, sorry, I didn't realize my mouse would do that. Whoa, okay, let's just stop and I'll talk about this for a second. I didn't mean to have both of those come up all at the same time. So because secant is 1 over cos, I end up with 1 over cos times 1 over sine. That's where this guy, this 1 over cos x sine x is coming from. That's just kind of expanding on this. And then I'm subtracting sine of x over cos of x. Okay, so then I looked at this and I said, okay, I'm subtracting fractions. When I subtract fractions, I need a common denominator. Common denominator is going to be cos x times sine x. So if I look at this guy, I'm missing the sine x. So in this next example that I brought up too quick, all I've done is I've multiplied this second fraction by sine x over sine x. That's going to give me the common denominator that I need. So I now have a common denominator of cos x times sine x. And on the top, I'm going to have 1 minus sine squared x. So 1 minus sine squared x over cos x times sine x. Now, this is a good one. 1 minus sine squared x is something. I want you to take a look at your, pause me if you have to think about it for a sec. I want you to take a look at your formula sheet and see if you can tell me what 1 minus sine squared x is. You were told on your formula sheet this statement, sine squared x plus cos squared x equals 1. Well, if sine squared x plus cos squared x equals 1, isn't it possible for me to subtract sine squared x from both sides and say that cos squared x equals 1 minus sine squared x? So we've gotten a new identity here. It's not really a new one, but it's a new way of writing it to say, hey, this also means that anytime I see 1 minus sine squared x, it is legal, it is totally fine for me to replace that with cos squared x. So I'm going to look at the 1 minus sine squared x that we have here and replace it with cos squared x. Now I'm looking at this. This is all multiplication happening, so I can divide the cos squared x by cos x here. That's okay to do because there's no addition or subtraction here. Where it gets dicey is when there's addition and subtraction, because now we don't have monomials that we're just multiplying or dividing. So cos squared x over cos x will leave me with 1 cos x on the top. So that's going to leave me with cos x over sine x. And we know that cos x over sine x is cotangent x. Okay? Awesome. Okay. Okay, so in our last example, I have 1 over 1 minus sine x plus 1 over 1 plus sine x. So here's a great example where the non-permissible values are not that same one that we saw for several examples. It's actually okay for sine of x to be 0 here. If sine of x was 0, I'd end up with 1 on the bottom. That's fine. And I'd end up with 1 on the bottom here. That's totally fine. What can't happen is sine of x can't be 1 here. Because if sine of x was 1, I'd end up with 1 minus 1, and that's 0. Over here, sine of x can't be negative 1, because I'd end up with 1 minus 1, and that would be 0. So my restrictions here are sine of x can't be plus or minus 1. Well, where is sine of x plus or minus 1? Remember, Calgary Stampede, sine is 1 or negative 1. I'm here or I'm here. So that's pi over 2 and 3 pi over 2. Notice it's not all of them this time. It's just the pi over 2 and the 3 pi over 2. So how we would say that is pi over 2 plus pi n, where n is a member of the integers. Now I need a common denominator. So I'm going to have to take the common denominator here will be both of those denominators multiplied together. So I need to take this guy and multiply it by 1 plus sine over 1 plus sine. And I need to take this guy and multiply it by 1 minus sine over 1 minus sine. Okay, so when I do that, I get this. Okay, so you can see my common denominators. I ended up with a 1 plus sine and a 1 plus sine on the top and bottom here that I needed. And then the 1 minus sine and the 1 minus sine on the top and bottom here that I needed. Okay, now I'm going to clean this up. If I'm looking at the top, I can now add the top together because I have common denominators. So I have 1 plus 1 is 2, and sine plus negative sine, that'll add up to be 0. So I just have a 2 on the top. On the bottom, I want to multiply these out. So I've got 1 times 1, 1 times sine x, neg sine x times 1, and neg sine x times sine x. Some of you may see that as a difference of squares. You may see that as conjugates and just go right to a squared minus b squared. Totally fine. However you do it, that doesn't matter to me. You should be able to end up with 2 over 1 minus sine squared x. Then, this is that exciting one again. Okay, go look at your formula sheet and see if you can tell me what 1 minus sine squared x is. 1 minus sine squared x is cos squared x, so now I'm left with 2 over cos squared x. Well, if I don't have to write this as a fraction, I don't want to. 1 over cos is secant, so 1 over cos squared x would be secant squared x. So my final answer here, I'm just going to write as 2 secant squared x. Okay, so again, the big important message here is think about this like a puzzle, okay? Think about, okay, what am I looking at? I'm going to look at my formula sheet, and I'm going to say, okay, what's on here to help me? Sometimes the only thing you can do is just do something that you see, and as you start doing little things that you see, the question will start simplifying out for you. Okay, so your job is to get through pages 240 to 246, and then in the next lesson, what we're going to start doing is looking at, in more specifics, what verification and what proving all entails. Until then, have fun doing some homework, and we'll see you soon. Take care, guys.